65 kilogram athlete in a long jump event leaps with a velocity of 7.5 meters per second at an angle of 30 degrees to the horizontal. For the following questions, treat the athlete as a point mass, ignore air resistance, and use G equals 9.8 meters per second squared. Do we know what a point mass is? We heard this? A couple of nods, yeah. So an actual athlete has mass in their torso, mass in their arms and legs, and it's just way too hard to calculate. A point mass just assumes all of the athlete's mass is at one spot in their body, right, in the center of their body. So it just makes the calculations easier. It's like approximating the athlete to be a ball, I guess. Okay. What is the athlete's velocity at the highest point? Okay. So, what's the first thing we probably should do here?
Diagram.
Draw a diagram. All right. So, our athlete jumps at an angle of 30 degrees, 7.5. Okay. Now the athlete's velocity at the highest point. There's the trajectory of the athlete. At the highest point, right there, what's the vertical velocity?
0.
0. Good. All right. So, if you just consider how the athlete is moving vertically, they go up. For a fraction of a second, they are not moving at the top, and then they move back down. Right? Up, back down. So, at their peak, they've sort of paused their vertical motion. They're not moving up or down, so their vertical velocity is 0 at that point. But we cannot assume their horizontal velocity is 0 there. Okay? They must still be traveling in the horizontal direction. So that's what we need to calculate. Now, what do we remember about horizontal velocity?
It's constant.
It's constant. It doesn't change because as long as there's no air resistance, we can assume that the horizontal velocity is constant. So if we can work out our horizontal velocity at the start, we're going to have our horizontal velocity at the top of that jump. So from that previous diagram, our horizontal velocity is equal to u cos theta, which is equal to 7.5 times cos 30. So our horizontal component of that velocity, I get 6.5, we'll call it. 6.5 meters per second. And that's it. So usually when you calculate a velocity, you need to work out the horizontal and the vertical components, put it into a triangle, and work out the hypotenuse. But in this case, at the peak, there is no vertical. So we just need the horizontal, which we work out like that. Does that make sense? Anything there not okay? Okay. Okay, what is the maximum height gained by the athlete's centre of mass during the jump? Okay, so if we're talking about maximum height and we can only work in one dimension at a time, which dimension are we working in? Vertical. Excellent. So let's work in our vertical dimension. So there's our 30 degrees, 7.5. So our initial vertical velocity is probably going to help us here. So our vertical velocity initially is going to be 7.5 times sine 30, which is 3.75. Now remember, when you're doing a projectile motion problem, it is really good to write down the letters that we know and the letters we want to know. Okay? So, we know UV. We know, well, what we would call U in our Suvat equations. So U, and remember we are just in the vertical plane here. U is 3.75. What else do we know? We know A. A is what? Negative 9.8. Good. So remember, we need to be aware of which way is up, which way is down. Makes sense in this case to have it looking like that. So positive is up, negative is down. So our initial velocity is up, so it's going to be positive. Our initial acceleration is down, so it's going to be negative. Do we know anything else?
V will be 0.
Correct. We know V is equal to 0. And what are we looking for? S. Okay. So we can do this. So again, you'd write down everything you know, everything you want to know, and you'd have a look at your formula sheet and you would see, right, we can use this formula. V squared equals U squared plus 2AS. So if we rearrange this, I'm going to get a little bit cramped in here, I apologise. So what have we got? V squared minus U squared on 2A. It's going to be equal to S. Is that right? V squared minus U squared over 2A. Yeah. Okay, so we can pop this in. So V squared is 0 minus U squared divided by 2 times 9.8. Well, 2 times negative 9.8, sorry, and that'll give us a positive. So S will be equal to 0.72 meters. All right, let's apply our common sense test. If you've got a long jumper, does that sound about right? They get 3/4 of a meter off the ground during a long jump? Sounds roughly right to me. Yeah. You just have to be careful of something that's really obviously wrong. So if you get 5 meters there, okay, that's the world's greatest long jumper. So, again, the best way to do these, draw up your diagram, make sure you know which direction is positive and which is negative, write down what you know and what you want to know, then find a formula that uses those letters. All right, they're your steps. Okay, next. Assuming a return to the original height, what is the total time the athlete is in the air? Okay, so we can work this out. We've got a lot of information from that last section that we can use. So first of all, a projectile travels in a mirrored path. Okay, the first half of this path will be exactly the same as the second half, but reversed. Okay, so if we want the total time for a projectile in flight, as long as it's landing where it started from, if you work out the time that it takes to get to its peak and double it, that'll give you the right answer. Okay, you don't have to worry, those two halves are exactly the same. They both take exactly as long and they take exactly the same amount of time. And in fact, if you worked out, well, 7.5, the velocity the ball hits the ground at over here will also be 7.5 at the same angle. It's an exact mirror image. Okay, assuming a return to the original height, what is the total time the athlete is in the air? So in this case, we want T. We know U. Let's still use that stuff from last time. We know V. And we know S. Oh, actually, no, we don't worry about S because we have A. So this is just for the first half of the flight, in the vertical plane again. Okay, so we're just looking, basically we're looking at how long it takes for the long jumper to get from their launch point to their highest point. So, I love this. I love when we have these letters because you can use this equation. And it just makes life so easy. So if we want to solve for T, T is equal to V minus U on A. Which is equal to, and again, our negatives should cancel out here. V minus U is negative 3.75 divided by negative 9.8. And we get 0.38 seconds. Yep, exactly. So that 0.38 seconds is the time it takes to get to their peak. Then we have to multiply it by 2 to get the time to go back down. So, my rounding's a bit off now, but if we multiply that by 2, so t total is equal to 2 times 0.38, and depending on how you round, or if you've left it on the calculator, you'll either get 0.77 or 0.76. Okay, common sense test. Think about the long jumpers you've seen on TV. So it makes sense they're in the air for about 3/4 of a second. Makes sense to me. That sounds reasonable. Okay, so there is the added wrinkle of finding the initial conditions. But once you have your initial conditions, these are exactly the same as you do the ones we did yesterday, on Friday, the horizontal projectiles. The only difference is those initial conditions where you need to use that diagram or trigonometry to find out the initial vertical and the initial horizontal velocities. Remember, only work in one plane at a time. Okay, you're either in horizontal or in vertical. Any questions? Okay, have a go at the next one.